Hi, hello, welcome. This is Discrete Mathematics, and today we are going to talk about section 1.1, sets and logic. In this section, we're talking all about sets. We're going to define sets. We're going to talk about different ways to write them, operations on sets, like different types of things we can do with sets, etc. So first, let's define what is a set. A set is a collection of objects. The objects in the set are called elements. So I'll write a couple of examples up here. The set X contains the elements 1, 2, and 3, which are numbers. So sets can contain numbers. Another set, let's call it Y, contains pancakes, waffles, and crepes. So sets do not have to contain only numbers. They can contain other items as well. They also don't have to have a finite number of items. So this one has 3 items. This one over here also has 3 items, but they can contain more items up to an infinite amount of items. We'll talk a little bit about how to count the items in a set in a little bit. So those are 2 examples of sets. Here we have another example, example 1. We want to consider the collection of numbers 0, 1, 2, 3, etc., all the way up to 9. So we're going to let set D be the set that contains 0, 1, 2, 3, all the way up to 9. This method of listing elements is called the roster method because I listed every single element in the set. If you have a relatively small number of elements in a set, this is a reasonable way to go. Another way that I can use to list the elements in a set is called set builder notation. And that's not necessarily listing the elements, it's describing the type of element that is in the set. So this one is D, which is the set of all X, such that, that's what this vertical bar means, such that X is a digit. So this would be any of these digits up here would be in this set D. This is set builder notation. Just a couple things to note before we move on. There are parentheses, which are used in things like ordered pairs. I'm sure you've seen parentheses before. There are also brackets. These are used in interval notation if you're describing an interval of values, and they're used other places as well. These are called brackets, sometimes, or square brackets. What we're using for sets are these curly braces. Curly braces. Sometimes we'll just call them braces. But this is what we use for sets. So that's what differentiates a set from some other type of thing that we're dealing with, is we use these curly braces. So let's talk about relations between elements and sets. So the notation that we're going to look at first is that A is in, little a is in big A. So that's another thing that we can talk about is little a, the lowercase letters are used to describe elements. Elements are lowercase and belong to capital A. So this is a set in upper case. So little a is in A, and that means that the lowercase letter a is an element in the set A. So I could write an example with that. I could say that 1, the element 1, is in the set 1, 2, and 3. I could also say that little a is not in A, which means A is not an element in the set. So I could say that 4 is not an element of 1, the set that contains 1, 2, and 3. So between the relation between an element and a set, we have this symbol, which is little a is in the set or little a is not in the set. So here we have example 2, where we're going to start talking about some standard sets. And these sets have an infinite number of elements in them. First up is the natural numbers, denoted with this n. And we're starting with the number 1, 2, 3, etc. Sometimes these are also called the counting numbers, because usually when you start counting with 1. Next up, we have the integers, which use Z, a capital Z. And notice there's like a little blank space between all of these. That's the special way that we denote these capital letters with their sets, is with this special Z. And integers, Z, why do they do that? It comes from the German word Zahlen, which means integer or number. So that's why we use a Z for that. But they have ... comma, -2, -1, 0, 1, 2, etc. So we're looking at all the positive numbers and 0 and all the negative numbers. So both of these are listed using the roster method. And we can actually use the roster method in this way with the ... meaning it goes on forever. So one thing you might be noticing is that, well, all of the natural numbers are included in the set of the integers, and you would be right. So we're going to draw a series of concentric circles here. So here's my first one, and I'm going to draw it small. This is the natural numbers. So that circle represents all the natural numbers. A little bit bigger than that is all of the integers. So all the natural numbers are included in the integers, although there are some integers that are not natural numbers, namely 0 and then all the negative ones. So we've got, we're building, slowly building our ring of concentric circles. Next up is the rational numbers, and for that we use Q. And Q comes from quotient, which is like a fraction. So rational numbers are the set that contains x such that x is p over q, where p and q are integers and q is not 0. So these are basically all the fractions. These are basically fractions. And this right here is an example of set builder notation. That's set builder notation. And so the rational numbers, when q is equal to 1, then this is just an integer over 1, which is that integer. So that's basically all of the integers. So here we're going to draw another ring on our circle, which is all of the integers. So that is q. Next up, we've got the real numbers, which we do r. And this r includes irrationals. That's where it's different from the other ones. Includes all the irrational numbers. So some common examples of irrational numbers are pi. The square root of 2 is irrational. The number e is irrational. And there are a bunch of other less popular, less common, less well-known irrational numbers. But this includes all of those irrational numbers, which cannot be written as fractions. So here is my r, real numbers. And we can also do these standard sets, but modify them a little bit. So here we have r plus in the superscript. So that's all the positive real numbers. Here we have z minus, which is all of the negative integers. So that would be all of these ones. Another common one that you'll see is, I'll write it over here, z and then non-neg up in the superscript, and that is all of the integers plus 0. So that's 0, 1, 2, 3, etc. So there's a little bit of roster method of listing a set. So it's basically all of the natural numbers plus 0, because 0 is neither negative or positive. So if we look at z negative or z plus, neither of those would include 0, because 0 is not positive or negative. So if you want all the positive ones plus 0, you can use this non-neg. Last one that we're going to talk about is complex numbers. Complex numbers include a plus bi, such that a and b are real numbers and I is the imaginary number, the square root of -1. If b happens to be 0, then you just have a, which is a real number. So that would be all the real numbers. But you can add to that some imaginary portion, which would be a complex number. So I've got my last circle to build up here. This is complex numbers. So this is an analogy that I like to use for this concentric circle situation is squares and rectangles. So all squares are rectangles, but not all rectangles are squares. There are some rectangles that are not squares, but every single square is a rectangle. So this is a much more complicated, we have many more levels than we do in our square and rectangle version. But this is kind of that similar idea. So those are some standard sets that we'll be using throughout this course. Okay, so I mentioned earlier that these sets have a finite number of elements in them. And we're going to be interested in how do you think about the number of elements in a set. And that concept is called cardinality. The cardinality of a set is the number of elements in the set. And we denote that with, they kind of look like absolute value symbols. It's a vertical bar. So if I have set A, which contains the elements 1, 2, 3, 4, and 5, then the cardinality of A is 5, because there are 5 elements in the set. One set that we haven't talked about, but that I'm going to talk about right now, is called the empty set or the null set, and that uses this symbol right here. It's like a 0 with a line through it. You can also just open your set, your curly brace, and then put nothing in it, and then close it. And that's also a way to denote the empty set. Although sometimes if you use this method, people might be confused. Did you forget to put something in there? Is there like a little mark in there and that's supposed to be a 1? So using this notation is a lot more common. You'll see that one to denote the empty set. So how many elements are in the empty set? 0. The cardinality of the empty set is 0. It contains no elements. That's its thing. That's what it is. Here we have a caution. Maybe I'll use a different color, green. So caution, if the set A is the set that contains the empty set, then the cardinality of A is 1, not 0, because we're not talking about the empty set. We're talking about a set that has one element, and that element is the empty set. So a set can be an element of another set, and we're going to explore that more on the next page. But basically what we're saying in this caution is that the empty set is an element of A, and if A has an element, then it has cardinality. So let's explore more the idea of a set can contain other sets. Scroll a little bit too far. Here we have example 3, part A. Set A is the set that contains 1 and the set that contains 2 and 8. So what is the cardinality of A, and is 8 an element of A? So if I'm looking at the elements in A, I have this one, and then I have this set as the second element. So A has 1, 2 elements. So the cardinality of A is 2. And the elements of A are 2. 2 is in A. Or sorry, not 2. 1. 1 is in A. And then the set that contains 2 and 8 is in A. But is 8 all by itself in A? And the answer is no. 8 is not an element of A. But the set that contains 2 and 8 is an element of A. So, no. Here's another set. B is the set that contains Z, which is the integers, Q, the rational numbers, and R, the real numbers. What is the cardinality of B? Well, we haven't talked about this yet, but the cardinality of the integers. How many integers are there? Well, there's an infinite number of them. What about rational numbers? Also, infinite number of those. Am I doing too many letters here? I think I am. Also an infinite number of those. What about real numbers? There's an infinite number of those, but there's like more of those than the other two. More infinite. So we're not really going to discuss this much in this course. It's beyond the scope, but these two have a countably infinite number of items in them, meaning you can count them. That's kind of, integers are countable because you see them and you count them. They really lend themselves well to counting. The real numbers are uncountable. So they are also an infinite number of those, but they are not able to be counted. So luckily for this problem, I actually don't really need to know any of these three. What I need to know is how many elements are in B. And B has 1 element, this whole set, 2 elements, that whole set, and this 3 elements, that whole set. So the cardinality of B is 3. So this whole thing over here was just kind of like an aside to think about when cardinality is infinite. And like I said, that's not going to be discussed much in this course, but that is a whole concept that's out there if you're interested in that. Okay. Other things to mention before we talk more about this table is that elements in a set do not repeat. So if I had something like the set that contains 1, 2, 1, and 3, I would not count this 1 twice. The cardinality of this set would not be 4. I don't even write the 1 twice. I should only write it 1 time. And also the order of the elements does not matter. So the set that contains 1 and 2 is the same as the set that contains 2 and 1. The standard convention is to write things in numerical order, but I mean, the set is not incorrect if you don't write it that way. But these two sets are not different sets. They contain all the same elements. Okay, let's look at some more notation. The relation between sets. Here we have A is equal to B. That means the two sets have the same elements. So in my example, I have the set of x such that x squared plus 2x minus 3 equals 0. And I want to know what set is that equal to. Well, in order to know that, I'd like to know what x values satisfy this first set. So I need to solve the equation. And I know that'll help me figure out which x values are actually in this set. So x squared plus 2x minus 3 equals 0. This is something that I could factor. X minus 1, x plus 3 equals 0. So x is 1 or negative 3. So this first set, the set of all x such that x squared plus 2x minus 3 equals 0, is the same as the set that contains negative 3 and 1. Next up is subset. A is a subset of B if every element of set A is also an element of set B. So let's say 1 and 2, that is a subset of 1, 2, and 3. Because all the elements of this left-hand set are in the right-hand set. Another thing that I could say, this is sort of like a less than or equal to, this subset notation. And so I could also say that the set that contains 1, 2, and 3 is a subset of the set that contains 1, 2, and 3. So all of the elements in this first set are in the second set. There's actually no elements that are not included, but that's okay with this subset notation. Next up is that A is not a subset of B. So that means there's some element in A that's not in B. So I could do an example here. Let's do the set that contains 1 and 4. That is not a subset of the set that contains 1, 2, and 3, because there is an element in A, that's the 4, that's not in B. Oops, not a subset. Next up, A is a proper subset of B. All the elements in A are also in B, but there is some element in B that's not part of A. So this one sounds a lot like subset, except for this last part. There must be some element that's in B that's not in A. So if I go back to the same example I used up there, 1, 2 is a proper subset of 1, 2, 3. But 1, 2, 3 is not a proper subset of 1, 2, 3, because there's no elements in this right-hand side that are not in the left-hand side. They're exactly the same. So this is kind of like a strictly less than, not or equal to. Whereas this subset case up here, we allow the or equal to. Okay, next one, the empty set or the null set, which we usually use one of these notations. This one's a little bit more common, 0 with a line through it, is the set that has no elements. And the empty set is a subset of every set. So the empty set is a subset of A. Let's see, A union B, or sometimes we write it as A or B. I like to remember it because this symbol right here kind of looks like the U from union. A union B or A or B is the set that contains all the elements that are either in A or B or both. So you're kind of cramming both sets together and getting rid of any duplicates. So if I was going to do, maybe I'll pick a new color. 1, 2, union, 2, 3. That would be the set that contains 1, 2, and 3. So this set has a 1, I'm going to include that. Both sets have a 2, so I'm going to include that, but I'm only going to include it once because I don't want to have any repeats. And then I'm going to include 3 because that second set had 3. So that's A union B, sometimes, or we write it as A or B. Next up is A intersect B, or A and B. And that's the set that contains only the elements that are in both A and B, the ones that they share. The way that I remember this one is that this intersect kind of looks like the N in the word intersect. The symbol looks like that N. So if I'm going back to the set that contains 1 and 2, intersect the set that contains 2 and 3, that is only going to be the set that contains 2. That's the only thing that's in both sets. Here I see it in this one, and there I see it in that one. Okay, last one on our list is A minus B. We can write it with the minus sign, or we can write it with the slash. Is set A minus set B. So that's all the elements that are in set A, but not in set B. So I'm going to come back and use my 1, 2, minus 2, 3. So I want all the elements of A, but I want to remove anything that's in B. So the thing that's in B is 2. So this is going to be just the set that contains 1. I'm not adding anything from B into A. I just am looking at what's in B, and if it shares anything in common with A, I'm removing that. Okay. Next up is the power set. The power set, and this is kind of written with a cursive or a curly P, which stands for power. The power set of A is the set of A that contains all of the subsets of A. So it's a set that contains all the subsets. So what is the power set of the set 1, 2, and 3? So the power set of A, we're saying this is set A, is the set that contains the empty set, because the empty set is a subset of every set. The set that contains just 1, the set that contains just 2, the set that contains just 3, the set that contains 1 and 2, the set that contains 1 and 3, the set that contains 2 and 3, and last up is the set that contains 1, 2, and 3. What is the cardinality of our power set? How many elements are in the set? 1, 2, 3, 4, 5, 6, 7, 8. Cardinality of the power set is 8. And let's take a look at that. Is there a special relationship going on there? And the answer is yes. Fact. Suppose A has n elements, then the cardinality of the power set is 2 to the power n. So in our example 4, we had 3 elements, 1, 2, and 3. And so the cardinality should have been 2 to the third power, which is 8. And that's exactly what we found. So how did we come about this? Well, let me draw a little graphic here. So let's say this is 1 element, 2 element, 3 element, all the way up to n elements. How many choices do we have for this first one? The first element can either be in the set or not be in the set. That's 2 choices. In the set, choices doesn't have an N. In the set or not in the set. In fact, all of these have 2 choices. To be in the set or to not be in the set. We're going to talk more about counting in chapter 6. So how many times are we doing this? 2 choices for the first one, and 2 choices for the second one, 2 choices for the third one. We're doing it n times. So that's where this 2 comes in. The choices are either it's included or it's not included. If this is something that's interesting to you, this whole counting idea, stay tuned for chapter 6. We'll talk more about that. Okay. Next up is the universal set. The universal set is the set of all elements under consideration. We usually denote the universal set as a U. It can be an infinite set, like Z or R, the real numbers, or the integers, or it can be a finite set. Now that we know that we have this idea of all the things we're considering, we can talk about a complement. A complement, and that's with the vertical bar over it, or sometimes we write it as A with a superscript C, is the universe minus A. So it's basically everything that's in the universe that's not in A. It's the opposite of A, and that is called the complement. Complement, not with an I, with an E, complement. So if I do an example here, let's say that U is the set that contains 1, 2, 3, 4, and 5. So this would be a finite example. And I'm going to say A is the set that contains 1 and 4. What is a complement? A complement would be everything in the universe that's not in A. So I'm looking at my universe. It contains 1, but that's an A, so I don't want to do that. But it does have 2 and 3. And then I don't want to include 4 because 4 is an A, and then it is 5. So A complement is 2, 3, and 5. Let's take a look at another example. Example 5. Consider the following sets where U, so that's our universal set, is 2, 3, 5, 7, 9, 11, 13, 17, and 19. A is the set that contains 2, and then you can read what B, C, D, and E are. Okay, so I want to do a few things. I want to insert the correct symbol, subset, not a subset, element, not an element. So just quickly over here, uppercase means set. And then also for sets, we're going to use proper subset or subset or not a subset. And then lowercase means element. And the things that we use for elements are is in the set or is not in the set, contains or does not contain. Okay, so in part A, so here we are with part A, I have B and E. B and E are both capital letters, so I'm going to use one of my subset. Is B a subset of E or is it not a subset of E? So I'm looking at B and I'm looking at E, and I'm seeing B contains 2 and 3, and E is 3, 5, 7, etc. So it looks like 2 is an element of B, but 2 is not an element of E. So B is not a subset of E because B contains an element that's not in E. Okay, let's take a look at B, 11 and D complement. So 11 is an element, so it is either going to be in the set or not in the set. This is D, 2, 3, 5, 7, and 9, and this is U. So D complement, maybe we should write down what that is. D complement is going to be everything that's in U that's not in D. So let's see, D has 2 and 3 and 5 and 9 and 7 and 9. So D complement is going to be 11, 13, 17, and 19. And I'm seeing that 11 is in D complement. 11 is an element of D complement. Next up, C and D. These are both capitalized, so these are both sets. So we're going to use subset or not a subset. Here's C and here's D. I'm looking 3, 5, and 7 are in C. 3, 5, and 7 are also in D. So C is a subset of D. C is also a proper subset of D. That's not one of our choices, but I just want to note that there are some elements in D, the 2 and the 9, that are not in C. Okay, next up, 3 and C complement. So we're going to be looking at an element again. C complement, let's figure out what that is. This is C, 3, 5, and 7. So that's what's not going to be included in C complement. So that's 2, and then 9, 11, etc. But that does not include 3. So 3 is not an element of C complement. I can see that 3 is an element of C. So if 3 is an element of C, it can't be an element of C complement because C complement doesn't include anything that's in C. So that's 2 different ways to think about that. One way is the way that I did first, which is writing what C complement is. And the other way was looking at, well, it's in C, so it can't be in C complement. Next up, I'm comparing 2 sets again. So I'm looking for a subset, not a subset. C is 3, 5, and 7, and E has 3, 5, and 7, and then some other stuff. So C is a complement of E. It's also a proper complement, or a subset. C is a subset of E. It's also a proper subset. Last one, 5, is that an element of C intersect E? Oh, so interesting. I'm going to have to do a little bit of extra work for this one. Here I'm looking for element or not an element. C intersect E. This intersect is the and, so it has to be in both C and E. So let's see. 3 is in both, 5 is in both, and 7 is in both. So 5 is in both. 5 is in C intersect E. Okay, so that is using some of those symbols. Next up, I want to find some of these sets. We're going to be dealing more with intersections and unions. So here I'm going to come down. This is kind of like part 2 of example 5. A, I want to find B intersect C complement. Let's see. So this is going to be B, which is 2, 3, intersect C complement. So C is 3, 5, and 7. So C complement is going to be 2, and then 9, 11, 13, 17, and 19. So B intersect that. They both have a 2, and that's it. So B intersect C complement is the set that contains 2. Next up is B, and we are doing D intersect E. So D is 2, 3, 5, 7, and 9. And E is 3, 5, 7, 11, 13, and 17. I'm going to choose my highlighter and find out where these have in common. So 2 is not in both, 3 is in both, and 5 is in both, 7 is in both, and that's it. So this one is 3, 5, and 7. Next up is C. B complement union D. Here we're finally doing a union. B complement is, let's see, B contains 2 and 3, and our universe contains a bunch of other things. So I want all those other things. 5, 7, 9, 11, 13, no 15, 17, and 19. That's B complement union D, which is 2, 3, 5, 7, and 9. So I want to write this union without writing any duplicates. So I'm going to do 2, and then 3, and then 5, 7, and 9, and then 11, 13, 17, and 19, which actually is everything. That happens to all equal U. Next up is D, which is A complement intersect E complement union D. Since this E complement union D is in parentheses, we're going to go ahead and do that first. So E complement union D is E complement. Oh, E has a lot of elements. 3, 5, 7, 11, 13, and 17. So E complement is 2, 9, and 19. Union D, which is 2, 3, 5, 7, and 9. So this complement is 2, 3, 5, 7, 9, and 19. The union is that. So now we want to intersect that with A complement. A complement intersect that thing right there. E complement union D is A complement, which is everything that's in U except for 2. 2, 3, oh no, sorry, except for 2. I just said except for 2, and then I wrote 2. 3, 5, 7, 9, 11, 13, 17, and 19. And intersect with this. 2, 3, 5, 7, 9, and 19. So let's see what they have in common. They both have the 3, and the 5, and the 7, and the 9, and the 19. Three, 5, 7, 9, and 19. That is working with unions and intersections with some finite sets. Okay, let's take a look at the last example on this page before we start talking about Venn diagrams. Consider the following sets. Insert the correct symbol. Either is a subset or is an element. So here we're doing more practice with sets versus elements. The set that contains X is a subset of the set that contains X. The set that contains X, is that a subset of this set? Well, yes, it is actually. Well, you know what? It looks like it's an element of that set. The set that contains X is an element of this set. It's right there, the one I highlighted in pink. But you know what? It's also a subset in this one. So it's actually both. It's an element of the set, and also X itself is an element of both sets. But the set that contains X is also an element. So this is a kind of a double whammy. Okay, next one. The set that contains 2, is that in the power set of the set 1, 2? So does the power set contain the element that is the set of 2? And it does. The power set, maybe we'll just write it here. The power set of 1, 2 is the set that contains the empty set, that's a subset of every set, the set that contains a 1, the set that contains a 2, and the set that contains 1 and 2. So here it is an element of this set.